This is the Algebra 2 Chapter 3.4 Linear Programming lesson. I apologize for my voice, but as you guys know, I'm a little sick, but I'm still going to proceed with making the video. The team challenge is a very important activity that we need to accomplish with our teams next class, so please remind me that we need to have that done because it will help lead into the linear programming problems. So linear programming is going to put together everything that you guys have learned about lines, inequalities, and solutions to systems. So you're going to be able to solve linear programming problems, and linear programming is a method for finding a minimum or maximum value that a function has that satisfies a given set of constraints. A constraint is one of the inequalities in the problem, linear inequalities. The solution region is called the feasible region. The minimum or maximum value of the objective function occurs at one of the vertices of this feasible region. I know this sounds complicated, but really it's not that complicated. So when you graph your system of linear inequalities, you will be shading, and where the shading overlaps in the first quadrant is the feasible region. That's where all possible solutions exist. Then you would find the vertices where the corner points that bound the feasible region, and those are shown here in blue, and you would plug them into what's known as the objective function to figure out the minimum or maximum. So this is just kind of a little picture of it. So we're going to do one on the next page. So a ski manufacturer makes two types of skis, downhill and cross country. Clearly those are going to be our variables. A pair of downhill skis requires 8 hours of fabrication and 1 hour finishing. A cross-country skis require 4 hours of fabrication and 1 hour of finishing. The fabrication department has no more than 112 hours of labor available per day, whereas the finishing department has no more than 24 hours of labor available per day. It sounds complicated, but it's not. So first we need to define our unknowns. Our unknowns are right here, the number of downhill and cross-country skis that we are going to figure out. What is the number of downhill and cross-country skis that the manufacturer can make? So we're going to write, it doesn't matter which one you use for X and Y, but I'm going to use X equals the number of downhill skis, and Y is the number of cross-country. And I'm going to use the shorthand for CX. So now you have to write the constraints. There are two constraints here that are listed. The one first is about fabrication. So I'm going to highlight everything that deals with fabrication. So 8 hours of fabrication for downhill, and cross-country requires 4 hours of fabrication. And there's no more than 112 hours of fabric. Let's see, yep, the fabrication department has no more than 112 hours of labor per day. So right there is our constraint. We need to write that constraint, and I've labeled that constraint total fabrication hours. So we've got 8 hours for downhill, so that'd be 8 times X, because X is the number of downhill skis. So it's 8 hours for every pair of downhill skis, plus 4 times Y, 4 hours for every pair of cross-country skis. And we've got no more, that means less than or equal to 112 hours. Now we always want to simplify these constraints because they're going to be much easier to graph. These are all three coefficients, these two coefficients are divisible by 4, and this constant is divisible by 4. So I'm going to rewrite this after dividing everything by 4. Best to have it in the most simplified version. All right, so there's our fabrication constraint. Next that we're going to do is, in blue, is the hours of finishing, and I'm going to do that in blue. Downhill skis require 1 hour of finishing, as do cross-country skis require 1 hour of finishing. And the finishing department has no more than 24 hours of labor per day. So now we're going to write the constraint, which I've labeled total finishing hour. There's 1 hour for every downhill, and there's 1 hour for every cross country, and it's less than or equal to 24. Now you don't need those ones in front of the variables, so I'm just going to rewrite them without the ones. So there are constraints. Truly, that's one of the hardest things to write, is pulling those from the problem. But you're trying to look for like the topics related to the variables, and then if you can label the topics of the constraints in general, you can write them. So our skis always have to be, number of skis always have to be positive. So x has got to be greater than or equal to 0, and y has got to be greater than or equal to 0. Our number of skis has to be positive, which basically means we're only working in the first quadrant. So next thing you would do is you would graph the feasible region. So you'd graph your two constraints, and you would, the feasible region where the shading overlaps, and then you would identify the vertices of the feasible region, or the corner points, and you can verify that you have the correct feasible region by testing a point, and you could also find the vertices by solving the system. But these are going to work out, I think, pretty nicely, and we'll check that we have the right vertices. So I want you to graph the feasible region. When I come back on the next video, I'll have this done for us, and I want you to list the vertices. There'll be 3 vertices. So graph the feasible region and try to identify the vertices, and then we'll go from there.